All right, we've got one more example here. Example 5 is to solve the initial value problem y prime of x is equal to x squared y, and y of 0 is equal to 7. So my y prime there, since we're going to treat this as a separable differential equation, I'm going to write that as dy dx is equal to x squared y. I'm not going to worry about that initial condition yet. That'll come in at the very end, is when you actually use the initial condition to solve for whatever arbitrary constant you find. So in the meantime, what I'm going to try to do is try to separate all the y's onto one side and all the x's onto the other. So that's just a matter of multiplying and dividing. If I divide both sides by y, get dy over y on the left, multiply both sides by dx, I get x squared dx on the right. And now I have successfully separated the y's on the left and the x's on the right, so I can integrate both sides. And so the integral of dy over y is natural log of absolute value of y. Integral of x squared is x cubed over 3. Now, just did my integration, so I've got to add on a constant right now. That's very important that you add on that constant right when you do the integration, not earlier, and definitely not later at the end. So now I'm going to try to solve for y. I'm going to raise e to both sides. E to the natural log of absolute value of y is equal to, be very careful here, e to all of the right-hand side, x cubed over 3 plus c. That all gets put in the exponent of e, not just the x cubed over 3 part. And so I've got absolute value of y is equal to, now my laws of exponents here tell me that this is e to the x cubed over 3 times e to a constant, not added to e to a constant, but multiplied by e to a constant. And so y is equal to plus or minus e to a constant. Think of that as a single constant, e to the x cubed over 3. And so if I think of that as a single constant, I'm going to write that as k times e to the x cubed over 3, because e to a constant is still a constant, and plus or minus a constant is still a constant. So I've got y equals e to the k e to the x cubed over 3. Now that's the general solution to my differential equation. It's as much as I can derive just using the differential equation. However, I've also got the initial condition. I've been given that, and so I'm going to use that to go a little bit farther and figure out the particular value of that constant. So if we hadn't been given that initial condition, we would just stop right now with the general solution. But since we have that initial condition, y of 0 is equal to 7. So I plug in y is equal to 7 and x is equal to 0. 7 for y and 0 for x, 0 cubed over 3. But e to the 0 is just 1, so that's equal to k. So I get 7 is equal to k. And if I plug that back into my general solution, now that I know what k should be, I get y is equal to 7e to the x cubed over 3. So that is my particular solution to the initial value problem. It's a solution to the differential equation and to the initial condition that we're given. And let me emphasize here that it was really key that I added the plus c on when I did the integration. I couldn't do it at the end, at this step right here at the end, like you would in a Calculus 1 problem or a Calculus 2 problem. Calculus 1, you just tack on a plus c at the end and everything's fine. Here you got to add the plus c right when you do the integration, and then what happens is that c gets kind of tangled up in the equation after that. So let me go through those steps again, just to make sure that they all make sense to you. I wrote y prime as dy dx. That's a very common technique for separable differential equations. And that's still equal to x squared y. I'm going to try to cross multiply and cross divide to get all my x's on the left. My x's are going to be on the right and my y's are going to be on the left. So if I divided that y over to the other side and I multiplied the dx over to the other side, and now I get this nice separated form with dy over y and x squared times dx. So I've got all x's on one side, all y's on the other. And I can integrate both sides. Integral of dy over y is natural log of y. The integral of x squared is x cubed over 3 plus c. Got to add that c when we integrate. And then in all the steps after that, you got to keep track of what's happening to the c. You can't just tack that c on at the end. So to undo that natural log, I raised e to both sides, so that gave me just absolute value of y on the left. On the right, it gave me e to the quantity x cubed over 3 plus c. Now you can't write that as e to the x cubed over 3 plus c. That's not the same thing. So that would be very bad. It's also not equal to e to the x cubed over 3 plus e to the c. That's also bad. It's really, we're using the laws of exponents here. X to the a plus b is equal to x to the a times x to the b. So this is e to the x cubed over 3 times e to the c. So I pulled that over to the other side. And because I had an absolute value here, I just made it plus or minus. But that whole thing, plus or minus e to the c, is just one big constant that I called k. And in order to find the value of k, I used the initial condition. This is telling me right here that x equals 0, y is equal to 7. So I plugged those values into this general solution here. Y was 7, x was 0. And e to the 0 is just 1, so this just turns into k is equal to 7. So I figured out my k is 7, plug that back into the general solution, and I get my specific solution, y is equal to 7 e to the x cubed over 3. So that wraps up our lecture on separable differential equations. I hope you've enjoyed it as much as I have. And we got lots of other lectures available on lots of other topics in differential equations. This is kind of just the very first topic. We got all kinds of stuff available on systems of differential equations, on solving differential equations by series. We've got stuff on second order differential equations, all the different solution techniques that you're going to learn in any differential equations course. We've got some stuff on numerical solutions of differential equations. We've even got partial differential equations in Fourier series. Got lectures for all of it. They're all here in the differential equations lecture series on Educator.com. So I hope you'll stick around and join me for all those other lectures and enjoy learning differential equations with me. So my name is Will Murray, and this is the differential equations lecture series here on Educator.com. Thanks for being with us. Bye-bye.